Alpha Centauri is the nearest star system to our Sun. Every astronomy textbook will tell you it is only 4.24 light-years away. That number sounds small. It sounds manageable. It sounds like a reasonable first destination for an interstellar civilization. It is none of those things. When you convert that distance into kilometers, you get approximately 40 trillion. When you calculate how long our fastest spacecraft would need to cross that gap, the answer is over 70,000 years. When you realize that even at 20% of light speed, the journey still takes more than 2 decades, and the return signal takes another 4 years, the number stops sounding small. The nearest star is not close. It is a wall, and this is what that wall actually looks like. If you enjoy having your sense of cosmic scale permanently recalibrated, do me a favor and hit that like button. And if you want more journeys like this one, subscribe to the channel. It really does help more than you think. Now, let's begin. There is a star system that every astronomy student learns about in the first week of class. It appears in every introductory textbook, on every star chart, in every documentary about the search for life beyond Earth. It carries a name that most people with even a passing interest in space have heard at least once. Alpha Centauri, the nearest star system to our own. It sits in the southern constellation of Centaurus, visible as one of the brightest points of light in the night sky for observers south of about 40 degrees north latitude. To the unaided eye, it looks like a single brilliant star. Through a modest telescope, it resolves into 2 distinct suns orbiting each other in a slow gravitational waltz that takes roughly 80 years to complete. These 2 stars are called Alpha Centauri A and Alpha Centauri B. A third companion, far dimmer and much farther from the pair, is a small red dwarf called Proxima Centauri. Together, they form a triple star system, and that system holds a title that sounds almost inviting: the closest stars to our Sun. Alpha Centauri A is remarkably similar to our Sun. It is a G-type main sequence star, just slightly more massive, slightly larger, and slightly more luminous. If you could stand on a planet in its habitable zone, the star overhead would look and feel almost familiar. Alpha Centauri B is a K-type star, somewhat smaller and cooler than the Sun, but still a respectably bright stellar furnace in its own right. The 2 orbit each other at distances that vary between roughly the orbit of Saturn and the orbit of Neptune in our own solar system, swinging closer and farther apart over their 80-year cycle. Together, they form a binary pair that has been gravitationally bound for billions of years, likely about the same age as our Sun, somewhere around 4.5 to 5 billion years old. Then there is Proxima. Proxima Centauri is a red dwarf with only about 12% of the Sun's mass and a tiny fraction of its luminosity. It is so dim that despite being the closest individual star to Earth, it is completely invisible to the naked eye. You need a decent telescope just to see it. Proxima orbits the Alpha Centauri A and B pair at an enormous distance, roughly 13,000 astronomical units away from them, taking somewhere around 500,000 years to complete a single orbit. For a long time, astronomers were not even certain Proxima was gravitationally bound to the central pair at all. It was only in 2017 that radial velocity measurements confirmed the connection. Proxima is a member of the system. It is just a very distant, very faint one. Proxima Centauri currently holds the title of the nearest star to the Sun. Its distance from Earth is approximately 4.24 light-years. Alpha Centauri A and B are slightly farther at approximately 4.34 light-years. The difference is small, roughly 1/10 of a light-year, because Proxima happens to be on the side of its vast orbit that faces us. This arrangement is temporary on cosmic timescales. Over tens of thousands of years, Proxima will drift in its orbit around the central pair, and eventually Alpha Centauri A or B will take turns being the closest star to our Sun. But right now, today, Proxima holds the record. 4.24 light-years, the nearest star. Say that number out loud. 4.24 light-years. It has a clean, compact sound. It fits neatly into a sentence. It is easy to remember and easy to repeat. Compared to almost any other distance in astronomy, it sounds small. The Milky Way is roughly 100,000 light-years across. The Andromeda Galaxy is 2.5 million light-years away. The observable universe spans 93 billion light-years. Against those numbers, 4.24 sounds almost neighborly. It sounds like the kind of distance an ambitious civilization might reasonably plan to cross. It sounds like a starting point, a first step, an achievable goal. This is the illusion, and it is one of the most dangerous illusions in all of space science, because 4.24 light-years is not small, it is not manageable, it is not a reasonable first step. It is a distance so enormous that the human brain lacks the wiring to process it honestly, and the language of astronomy actively conspires to make it sound more approachable than it is. Let us begin dismantling that illusion with the most basic conversion available. 1 light-year is the distance that light travels in 1 year, moving at approximately 299,792 kilometers per second. In 1 year, light covers roughly 9.46 trillion kilometers. Multiply that by 4.24, and the distance to Proxima Centauri comes out to approximately 40.1 trillion kilometers. Written out in full, that is approximately 4,100,000 billion kilometers. In miles, it is roughly 25 trillion. In astronomical units, the standard measure where 1 AU equals the distance from Earth to the Sun, Proxima Centauri, sits at roughly 268,000 AU. These numbers are already beyond intuitive comprehension, but they still feel abstract. They are too large to mean anything without context. So let us build some context, piece by piece, starting with the one speed that every human being intuitively understands as fast. Light is the fastest thing in the universe. Nothing that carries information or mass can travel faster. A beam of light covers the distance from Earth to the Moon in about 1.3 seconds. It reaches the Sun in about 8 minutes and 20 seconds. It passes the orbit of Neptune, the outermost major planet, in roughly 4 hours. Light is so fast that it can circle the entire Earth 7.5 times in a single second. There is no speed more extreme, no velocity, more absolute, and light needs 4 years and roughly 3 months to reach Proxima Centauri. Think about what that means. A photon leaving Earth right now, travelling at the absolute maximum speed that physics permits, will not arrive at the nearest star until sometime in the year 2030. If you shone a flashlight toward Proxima Centauri tonight, the first photon from that beam would arrive after the next United States presidential term has ended, after the next Olympics have been held, after thousands of news cycles have come and gone, and that is the fastest possible crossing. Nothing with mass can match it. Nothing ever built by humans has come close. Now let us try to grasp the emptiness that fills those 4.24 light-years. Space between stars is not simply far. It is empty in a way that nothing on Earth can prepare you for. The average density of interstellar space in our region of the galaxy is roughly 1 atom per cubic centimetre. That is a vacuum so deep that the best laboratory vacuum chambers on Earth are millions of times denser. Between here and Proxima Centauri, there is almost nothing. No gas clouds of any significance, no rogue planets that we have detected, no asteroids, no comets, no waypoints, no landmarks. Just an expanse of near-perfect emptiness stretching for 40 trillion kilometers. To get a sense of this scale, imagine shrinking the entire solar system down so that the Sun is a basketball sitting on the center line of a football field. At this scale, Earth would be a small grain of sand about 26 meters away. Jupiter would be a marble at roughly 130 meters. Neptune, the most distant major planet, would be a small pebble about 3/4 of a kilometer from the basketball. The Voyager 1 spacecraft, the most distant human-made object, would be a microscopic speck roughly 4.5 kilometers from the basketball after nearly 50 years of continuous travel. At this same scale, Proxima Centauri would be another basketball sitting approximately 7,000 kilometers away. That is roughly the distance from New York City to Rome. The entire solar system, everything humanity has ever visited or even sent a probe to, occupies a region that fits within a few kilometers of the basketball. The nearest star is on another continent, and between those two basketballs, across those 7,000 kilometers of scale model distance, there is nothing. No structure, no rest stop, no intermediate destination. Just the equivalent of crossing the Atlantic Ocean and most of Western Europe with nothing beneath you but empty vacuum. This is the reality that the phrase 4.24 light-years conceals. It sounds like a number you could work with. It is actually an abyss. There is another way to appreciate the gap. Consider the signals we use to communicate with our most distant spacecraft. Voyager 1, launched in 1977, is currently the farthest human-made object from Earth. As of early 2026, it is approximately 172 astronomical units from the Sun, which is roughly 25.7 billion kilometers. A radio signal from Earth reaches Voyager 1 in just under 24 hours. In fact, in November of 2026, Voyager 1 is projected to cross the milestone of being one full light day from Earth for the first time. That is worth pausing on. The most distant object humanity has ever created, after nearly 5 decades of non-stop flight at roughly 17 kilometers per second, is about to reach the point where a message from Earth takes a single day to arrive. Proxima Centauri is approximately 1,550 light days away. Voyager 1, after almost 50 years of travel, has covered roughly 0.06% of the distance to the nearest star. If you drew a line on a football field to represent the full distance to Proxima Centauri, Voyager's progress since 1977 would be a mark barely 6 centimeters from one end of the field. The width of 2 fingers on a 100-yard line. That is not a metaphor. That is the arithmetic. The emptiness between here and Alpha Centauri is not a gap in the way that an ocean is a gap, or a desert is a gap. An ocean has currents and islands and weather systems that break the distance into manageable pieces. A desert has oases and horizons, and the reassurance that on the other side lies something reachable within a human lifetime. The interstellar void offers none of that. It is a gap with no features, no milestones, no intermediate scale. It is pure distance, undiluted by anything that might make it feel crossable. And here is what makes this distance especially deceptive. Alpha Centauri is bright. It is the 3rd brightest star system in the entire night sky, outshone only by Sirius and Canopus. For observers in the southern hemisphere, it blazes overhead with a combined apparent magnitude of roughly minus 0.27, making it a prominent and unmissable feature of the sky. You can step outside on a clear night in Sydney or Santiago or Johannesburg and see Alpha Centauri without any optical aid at all. It looks close. It looks like a neighbour. The sheer brilliance of its light creates an instinctive sense that the source cannot be far away. But what you are seeing when you look at Alpha Centauri is light that left the system over 4 years ago. The photons entering your eye departed Alpha Centauri A and B, when the calendar on Earth read 2021 or 2022. You are not looking at the stars as they are. You are looking at where they were and how they shone years before the present moment, and that temporal gap is itself a measure of the distance. Every year of light travel time represents 9.46 trillion kilometers of empty space that the photons had to cross before they could reach your retina. The brightness is misleading in another way too. Alpha Centauri A is intrinsically a fairly luminous star, about 1.5 times the luminosity of the Sun, but the reason it appears so bright in our sky is primarily its proximity. Move Alpha Centauri to 10 parsecs, the standard distance used for measuring absolute stellar magnitude, and it would dim to an unremarkable apparent magnitude of about 4.38 for the A component alone. It would be a faint, forgettable star in a crowded sky. Alpha Centauri's brilliance is an artifact of its nearness, and that nearness, in absolute physical terms, is still 40 trillion kilometers. Humans evolved to judge distance by visual cues. Bright objects appear closer, dim objects appear farther. This heuristic works well on the African savanna, where the brightness of a fire reliably indicates how far away the campsite is. It fails catastrophically in astronomy. Sirius, the brightest star in the night sky, is almost twice as far away as Alpha Centauri. Canopus, the second brightest, is over 70 times farther. The relationship between brightness and distance in the stellar realm is dictated by intrinsic luminosity, not by proximity, and our evolved visual instincts are worse than useless for interpreting what we see. When you look at Alpha Centauri and feel that it is close, your brain is applying a rule that breaks down the moment you leave Earth's atmosphere. Let us also address the scale problem from the direction of time. Humans have been aware of Alpha Centauri as a star for thousands of years. Ancient navigators in the southern hemisphere used it as a reference point, but we have known its distance for less than 2 centuries. In 1832, Thomas Henderson at the Royal Observatory at the Cape of Good Hope began the painstaking positional observations that would eventually yield the first measurement of Alpha Centauri's parallax, the tiny apparent shift in the star's position caused by Earth's orbit around the Sun. Henderson calculated a parallax that implied Alpha Centauri was astonishingly far away, so far that he initially withheld his results because he suspected they were too large to be correct. He eventually published in 1839, after Friedrich Bessel had announced a parallax measurement for 61 Cygni the previous year. Henderson was right. Alpha Centauri was not a nearby lantern. It was a distant sun separated from our own by a void that no human technology of the era could even begin to contemplate crossing. Nearly 2 centuries later, we have measured that distance with extraordinary precision using spacecraft like the European Space Agency's Gaia Observatory, which has refined stellar parallaxes to an accuracy of millionths of an arcsecond. The current best measurement places Proxima Centauri at a parallax of 771.64 milliarcseconds, corresponding to a distance of 4.2465 light-years. We know exactly how far away it is. The number is not uncertain. The number is not approximate. The distance is established to a precision that Henderson could not have dreamed of, and that precision changes nothing about the fundamental problem. Knowing the distance to within 100th of a light-year does not make the distance shorter. It does not make the void less empty. It does not bring the nearest star 1 kilometer closer to our reach. Precision of measurement and accessibility of destination are completely unrelated, and Alpha Centauri demonstrates this with merciless clarity. There is one more dimension to the illusion that must be addressed before we move on. It is the word nearest itself. In everyday language, nearest implies accessibility. The nearest grocery store is one you can drive to. The nearest hospital is one you can reach in an emergency. The nearest friend is one you can visit on a weekend. The word carries a built-in assumption that proximity translates to reachability. In astronomy, it does not. The nearest star is not the reachable star. The nearest star is simply the least unreachable star. The difference matters enormously, and it is a distinction that popular science writing almost never makes explicit. Proxima Centauri is the closest star to our Sun. It is also, by any engineering metric currently available to human civilization, completely and utterly out of reach. Not difficult to reach. Not expensive to reach. Not impractical to reach. Unreachable. The technology to send a functioning spacecraft to Proxima Centauri and have it arrive within a human lifetime does not exist. It is not under construction. It is not in a testing phase. The fundamental propulsion systems that would be required to make the crossing in less than several thousand years have not been built at any scale by any nation for any purpose. The nearest star is a destination we can see, measure, characterize, and study in extraordinary detail from a distance of 40 trillion kilometers. But we cannot go there. This is the core of the illusion. Alpha Centauri occupies a strange and uncomfortable position in the human understanding of space. It is close enough to see with the naked eye. It is close enough to measure with high precision. It is close enough that we have already detected planets around one of its component stars. But it is far enough away that no propulsion system ever tested by humanity could deliver a spacecraft to its vicinity within the span of recorded human history. It is simultaneously the most accessible and the most inaccessible destination in the galaxy. It is the nearest star, and it is nowhere near. The Alpha Centauri system is not merely a point of light in the southern sky. It is a test case. It is the simplest version of a problem that scales up mercilessly for every other star in the galaxy. If we cannot grasp the distance to the nearest star, we cannot grasp interstellar space at all. If we cannot conceive of a realistic mission to Alpha Centauri, then every other stellar destination is even more hopeless. The distance to Alpha Centauri is the floor of interstellar travel, the absolute minimum challenge. Everything else is harder, and the floor is already impossibly high. We know the numbers. We know the distance in kilometers, in astronomical units, in light years. We know how long light takes to cross the gap. We know how little of that gap our fastest spacecraft has covered in half a century of flight. We know the void is empty, featureless, and unbroken by any landmark or waypoint. We know the star is bright and visible and close in astronomical terms, and impossibly remote in engineering terms. But numbers alone do not convey what this distance means for an actual mission. To understand why Alpha Centauri is not just far but terrifyingly far, we need to stop measuring and start moving. We need to ask what happens when you point a real spacecraft at the nearest star and push the throttle as hard as current technology allows. The answer is where the true horror begins. Let us now do something that most discussions of Alpha Centauri avoid. Let us stop talking about the distance as a number and start treating it as an engineering problem. Not a theoretical problem, not a thought experiment. A real problem, with real spacecraft, real velocities, real power sources, and real material constraints. The moment you do this, the distance transforms from an abstract figure on a page into something that feels physically hostile. The fastest object humanity has ever sent on a trajectory out of the solar system is Voyager 1. Launched on September 5, 1977, Voyager 1 completed its primary mission of studying Jupiter and Saturn, and then continued outward, using gravitational assists from both giant planets to boost its velocity to approximately 17 kilometers per second relative to the Sun. That is roughly 61,200 kilometers per hour, or about 38,000 miles per hour. As of early 2026, Voyager 1 is approximately 172 astronomical units from the Sun and is the most distant human-made object in existence. 17 kilometers per second is fast by any human standard. It is more than 15 times the speed of a rifle bullet. It is roughly 50 times the speed of sound at sea level. If you could sustain that velocity on Earth's surface, you would circumnavigate the planet in roughly 39 minutes. Voyager 1 crosses a distance equal to the diameter of Earth every 12.5 minutes. It covers the distance from Earth to the Moon in about 6 hours. It is, by the standards of anything humans have ever built, extraordinarily fast. Now, point it at Proxima Centauri. The distance is approximately 4.24 light-years, which converts to roughly 268,000 astronomical units, or about 40 trillion kilometers. At 17 kilometers per second, Voyager 1 would need approximately 74,000 years to cover that distance. 74,000 years. That is not a travel time. That is a geological epoch. 74,000 years ago, modern humans had not yet left Africa in significant numbers. The most recent ice age had not yet reached its maximum extent. Agriculture did not exist. Writing did not exist. Cities, nations, empires, all of recorded civilization occupies a window of roughly 5,000 to 6,000 years. Voyager 1 would need more than 12 times that span to reach the nearest star. But Voyager 1 is not actually heading toward Alpha Centauri. Its trajectory carries it in a completely different direction, toward the constellation Ophiuchus. and the nearest star it will approach is an obscure red dwarf called Gliese 445, which it will pass in roughly 40,000 years at a distance of about 1.7 light-years. Voyager 1 was never designed to reach another star. It was designed to study Jupiter and Saturn. The fact that it is still functioning and still transmitting data after nearly 50 years is a remarkable engineering achievement, but its velocity and direction have nothing to do with interstellar travel. It is simply the fastest thing we have ever flung outward, and it makes a useful benchmark for understanding why present technology is so desperately inadequate for crossing interstellar distances. Let us try other spacecraft to see if the picture improves. New Horizons, the probe that flew past Pluto in July of 2015, is currently travelling at roughly 14.5 kilometers per second relative to the Sun, slower than Voyager 1. At that speed, the journey to Proxima Centauri would take approximately 87,000 years. That is worse, not better. New Horizons is a more modern spacecraft than Voyager, built with decades of additional engineering experience, but it is actually slower on its outbound trajectory because it received less favourable gravitational assists. What about the Parker Solar Probe, often cited as the fastest spacecraft ever built? Here the numbers require careful handling. Parker Solar Probe achieves its record-breaking speeds not on an outbound trajectory but during close passes of the Sun, where it dips deep into the solar gravitational well and accelerates to extraordinary velocities at perihelion. At its closest approach, Parker Solar Probe has reached speeds exceeding 190 kilometers per second relative to the Sun. That is more than 11 times faster than Voyager 1. It sounds like a breakthrough. It is not. Parker Solar Probe's extreme velocity occurs only at the bottom of its elliptical orbit, deep inside the Sun's gravity well. As the probe climbs back outward on its orbit, it slows down dramatically, trading kinetic energy for gravitational potential energy, the same way a ball thrown upward slows as it rises. Parker Solar Probe cannot maintain 190 kilometers per second on a straight-line trajectory away from the Sun. That speed is borrowed from the Sun's gravity and must be returned. If you could somehow extract Parker Solar Probe from its orbit at perihelion and send it on a straight-line escape trajectory, the velocity it could maintain would be far lower, subject to the same constraints of gravitational escape that limit all outbound spacecraft. Even if we could hypothetically sustain Parker Solar Probe's peak perihelion speed of 190 kilometers per second for an entire interstellar crossing, the travel time to Proxima Centauri would still be approximately 6,700 years. That is longer than all of recorded human history, longer than the span from the invention of writing to the present day. And this is using a speed that no spacecraft has ever sustained, and that no current technology can maintain outside a close solar pass. The arithmetic is relentless. At 100 kilometers per second, a speed no outbound spacecraft has achieved, the journey takes approximately 12,700 years. At 500 kilometers per second, a speed that exists nowhere in current engineering, the trip still requires about 2,500 years. Even at 1,000 kilometers per second, a velocity so extreme that no propulsion technology under development can produce it for a spacecraft of any meaningful size, the crossing takes roughly 1,260 years. Every speed you try, every optimistic assumption you make, the answer comes back in centuries or millennia. The distance does not negotiate. Let us consider what these timescales mean for mission design, because the problem is not merely that the journey takes a long time. The problem is that nothing about a spacecraft or a mission architecture can survive the durations involved. Start with materials. Every spacecraft ever built has a finite structural lifetime. Components degrade, metals fatigue, seals lose integrity, lubricants evaporate in vacuum. Radiation slowly damages electronics, flipping bits in memory, degrading solar cells, weakening structural bonds. The most durable spacecraft ever built, the Voyager probes, are showing signs of age after less than 50 years. Their radioisotope thermoelectric generators are running low on power. Their instruments have been progressively shut down to conserve energy. Their data recorders use technology from the 1970s. Voyager 1 is still functioning, but it is functioning at the ragged edge of its engineered lifespan, held together by the ingenuity of ground controllers who send commands that take nearly a full day to arrive. Now imagine asking that spacecraft, or any spacecraft, to survive for 74,000 years. The engineering challenge is not difficult, it is absurd. No material humans have ever manufactured can maintain structural integrity for that duration without maintenance. No electronic system can operate for millennia without failure. No power source we currently possess can provide energy for more than a few centuries at most. Radioisotope thermoelectric generators, the gold standard for deep space power, have half-lives measured in decades, not millennia. Solar panels are useless beyond the outer solar system where sunlight drops to negligible intensity. Nuclear fission reactors require fuel that decays and control systems that degrade. Every power technology we have runs dry on timescales vastly shorter than the transit time to Alpha Centauri at current speeds. Then there is the question of communication. Voyager 1 currently transmits data to Earth at a rate of roughly 160 bits per second, using a 23-watt radio transmitter and a 3.7-meter high-gain antenna. Even at its current distance of about 172 AU, the signal that arrives at Earth is so faint that it requires the enormous 70-meter dishes of NASA's Deep Space Network to detect. The signal strength falls off with the square of the distance. Double the distance, and the signal becomes 4 times weaker. At Alpha Centauri's distance of 268,000 AU, the signal from an identical transmitter would be roughly 2.4 million times fainter than it is right now. No existing radio telescope could detect that. Not the Deep Space Network, not the Green Bank telescope, not a hypothetical array, 10 times larger than anything currently built. The inverse square law is unforgiving. Maintaining communication with a spacecraft at interstellar distances requires either vastly more powerful transmitters, vastly larger antennas, or both. And those additions come with mass, and mass is the enemy of velocity. Every kilogram you add to the spacecraft is a kilogram you must accelerate to interstellar speed, and that requires more fuel, which adds more mass, which requires still more fuel. The rocket equation turns every additional gram of communication hardware into kilograms of propellant, driving the total mission mass upward in a vicious exponential spiral. Even if communication were technically possible, there is a more fundamental problem. At Voyager 1 speed, the spacecraft would be in transit for 74,000 years. Who is listening at the other end after 74,000 years? What institution maintains the receiving station? What civilization remembers the mission exists? The oldest, continuously operating human institutions are religious orders and universities that date back roughly 1,000 years. The oldest known human structures are about 12,000 years old. No human organization, government, religion, or cultural tradition has ever survived for 74,000 years. Not even close. Sending a spacecraft on a 74,000-year journey is not a mission plan. It is an act of faith in the permanence of civilization that has no historical support whatsoever. The obvious rebuttal arrives immediately. If no single human can survive the journey, why not send many? Why not build a vessel large enough to sustain a population across generations, a city in space, a self-contained world, hurtling through the void with families being born, living, and dying aboard while the ship creeps toward its destination. The concept is called a generation ship, and it has been a staple of science fiction for nearly a century. It sounds elegant. It collapses under examination. Start with biology. A population confined to a closed vessel for 74,000 years must maintain genetic diversity sufficient to avoid inbreeding depression, the gradual accumulation of harmful recessive traits that occurs when a small population reproduces within itself over many generations. Population genetics research, including studies published in the context of interstellar mission planning, suggests that a minimum viable population for a multi-generational voyage would need to number in the thousands, not hundreds. Some estimates place the threshold at roughly 4,000 to 5,000 individuals to maintain sufficient genetic diversity across centuries without aggressive genetic management. Others suggest that with careful breeding protocols the number could be reduced, but even the most optimistic figures require a starting crew of several hundred at absolute minimum, with strict reproductive controls enforced across every generation for the entire duration of the journey. Several hundred people is not a crew, it is a small town. A small town requires food production, water recycling, waste processing, medical care, education, conflict resolution, governance, and all the other systems that sustain a human community. Every one of these systems must function without external input for 74,000 years. No resupply, no replacement parts from Earth, no emergency imports of seed stock or antibiotics or rare minerals. The ship must carry or manufacture everything its population will ever need, across a span of time roughly 15 times longer than all of recorded human history. No closed ecological system has ever achieved anything remotely approaching this level of self-sufficiency. Biosphere 2, the most ambitious attempt to create a sealed, self-sustaining habitat on Earth, experienced critical oxygen depletion and crop failures within its first 2 years of operation. Despite being built on the surface of a planet with ample sunlight, stable gravity, and immediate access to emergency intervention, the International Space Station, humanity's most sophisticated space habitat, requires constant resupply from Earth, roughly several tons of food, water, equipment, and spare parts delivered by cargo spacecraft multiple times per year. A generation ship would need to replicate the ecological stability of an entire planetary biosphere using only the resources loaded aboard at departure, with zero margin for systemic failure across millennia. The engineering challenge is severe, the sociological challenge may be worse. A generation ship is not merely a technical system, it is a civilization. And civilizations do not remain static over thousands of years. Languages evolve, cultures shift, religions rise and fall, political systems transform, sometimes violently. The values, priorities, and even the basic worldview of a human population change dramatically over centuries. The people who board the ship at departure would share almost nothing culturally with the people who arrive at the destination tens of thousands of years later. The arriving population would not speak the same language as the founders. They would not share the same beliefs, the same social structures, or the same understanding of why the mission was launched in the first place. This raises a profound ethical question that generation ship proposals rarely address honestly. The founding generation chooses to board the ship. Every subsequent generation does not. They are born into a vessel they cannot leave, committed to a mission they did not choose, travelling toward a destination that will not be reached in their lifetimes, or their children's lifetimes, or their grandchildren's lifetimes. For hundreds of generations, every person aboard lives and dies in transit, never seeing either the origin or the destination. They are, in a meaningful sense, prisoners of a decision made by ancestors so remote that they have passed into mythology. What happens when the 35th generation decides the mission is pointless? What happens when a political faction seizes control of the ship and redirects its resources? What happens when a religious movement arises that reinterprets the mission's purpose or denies that a destination exists at all? Over 74,000 years, every conceivable social disruption will not merely be possible but statistically inevitable. Civil wars, famines caused by ecosystem failures, technological regressions, plagues sweeping through a confined population with no external medical support. The ship does not need to survive one catastrophe. It needs to survive all of them, in sequence, for longer than any civilization has ever existed on Earth. The generation ship is not a solution to the distance problem. It is a restatement of the distance problem in biological and sociological terms. Instead of asking whether a machine can survive for 74,000 years, It asks whether a human community can survive for 74,000 years inside a machine. The answer, based on everything we know about human societies, ecosystem engineering, and population genetics, is almost certainly no. Not because the idea is physically impossible, but because the timescale exceeds every known limit of human social and biological endurance by orders of magnitude. The distance to Alpha Centauri does not just defeat our machines, it defeats our species. At current speeds, the crossing is too long for electronics, too long for materials, too long for institutions, and too long for human populations confined in artificial habitats. The problem is not one of engineering or willpower. It is a problem of time, and at 17 kilometers per second, there is far too much of it. There is also the problem of navigation. Over a journey of 74,000 years, even tiny errors in velocity or direction compound into enormous deviations. A pointing error of 1,000th of a degree at departure would result in a missed distance of roughly 700 million kilometers at arrival, nearly 5 times the distance from Earth to the Sun. Mid-course corrections require functioning thrusters, functioning navigation sensors, and functioning onboard computers. All of these systems must work not just for decades but for tens of millennia. No thruster system retains propellant that long. No sensor maintains calibration over those timescales. No computer operates without failure for centuries, let alone millennia. And the interstellar medium itself poses hazards. While the space between stars is extremely empty by terrestrial standards, it is not a perfect vacuum. Dust grains, some no larger than a few microns, drift through interstellar space at relative velocities that depend on the spacecraft's speed. At 17 kilometers per second, a collision with even a tiny dust grain delivers energy proportional to the square of the velocity. Over 74,000 years, the cumulative probability of impacting a dust grain large enough to damage critical systems is not negligible. There is no shielding technology that can protect a spacecraft from every possible micro-impact over a journey of that duration. The interstellar medium is sparse, but time is abundant, and probability compounds. Let us now turn away from Voyager-class speeds and consider the fastest propulsion technologies that are realistically under development or within near-term engineering reach. Ion propulsion represents one of the more promising technologies for deep space missions. Instead of burning chemical fuel in a brief, violent burst, ion engines accelerate charged particles, usually xenon ions, using electric fields, producing a gentle but continuous thrust that builds velocity over time. NASA's Dawn spacecraft, which orbited the asteroid Vesta and the dwarf planet Ceres, used ion propulsion to achieve impressive velocity changes over its mission lifetime. But the exhaust velocities of ion engines, while much higher than chemical rockets, still top out at roughly 30 to 50 kilometers per second. Even with years of continuous thrusting, the final spacecraft velocity remains far below what is needed for interstellar travel. The most advanced ion propulsion concepts, such as the Variable Specific Impulse Magnetoplasma Rocket, or VASIM, promise higher exhaust velocities and greater efficiency. VASIMA could theoretically accelerate a spacecraft to higher velocities than conventional ion engines, but even the most optimistic projections for VASIMA-class systems produce spacecraft velocities well under 100 kilometers per second. At those speeds, the journey to Proxima Centauri still requires over 12,000 years. Ion propulsion is a superb technology for navigating the solar system. It is inadequate for crossing interstellar space. Nuclear thermal propulsion offers another avenue. In a nuclear thermal rocket, a nuclear reactor heats a propellant, usually hydrogen, to extreme temperatures and expels it at high velocity. This produces significantly more thrust than ion engines and higher exhaust velocities than chemical rockets. The NERVA program of the 1960s demonstrated that nuclear thermal rockets work. Modern successors are under development for potential crewed Mars missions, but the exhaust velocity of a nuclear thermal rocket, while impressive, maxes out at roughly 9 kilometers per second. That is actually slower than Voyager 1's current velocity relative to the Sun. Nuclear thermal propulsion is useful for shortening transit times within the solar system, but it does not come close to solving the interstellar speed problem. Nuclear pulse propulsion, the concept behind Project Orion from the late 1950s, envisioned detonating nuclear bombs behind a spacecraft and riding the shock waves. Theoretical calculations suggested that an Orion-style vehicle could potentially reach velocities of 3 to 5% of the speed of light, which would bring Proxima Centauri within reach in roughly 85 to 140 years. That is a dramatic improvement over 74,000 years, but Project Orion was never built. It was cancelled for reasons that ranged from the Partial Nuclear Test Ban Treaty of 1963, which prohibited nuclear detonations in space, to the staggering engineering challenges of building a pusher plate that could withstand repeated nuclear explosions. The concept remains theoretically interesting but practically non-existent. No hardware exists, no test has been conducted, no government or institution is currently funding an Orion-class vehicle. Nuclear fusion propulsion, a step beyond fission-based systems, has been studied in concepts like Project Daedalus, a 1970s British Interplanetary Society design study for an uncrewed interstellar probe. Daedalus envisioned igniting pellets of deuterium and helium-3 in a reaction chamber to produce exhaust velocities of roughly 10,000 kilometers per second, enough to accelerate a 450,000 kilogram payload to approximately 12% of the speed of light. At that speed, the trip to Proxima Centauri would take about 36 years. That is finally within a human lifetime. But Daedalus was always a paper study. The engineering challenges are formidable. Controlled fusion ignition of fuel pellets at the rate required, roughly 250 ignitions per second, has never been achieved in any laboratory. The fuel, helium-3, is extremely rare on Earth. The most accessible source is the lunar regolith, where it exists in concentrations of parts per billion, meaning you would need to mine and process millions of tons of lunar soil to collect enough fuel for a single mission. The spacecraft itself would be a colossus, massing over 50,000 metric tons fully fueled, larger than an aircraft carrier. Daedalus was designed not as a construction blueprint, but as a theoretical demonstration that interstellar travel was not impossible under known physics. It proved the principle. It did not solve the problem. The common thread across all these propulsion technologies is the same. Chemical rockets are hopelessly slow. Ion engines are elegant but insufficient. Nuclear thermal rockets barely improve the situation. Nuclear pulse propulsion could work in theory but is banned and unbuilt. Fusion propulsion could reach respectable interstellar speeds, but requires engineering breakthroughs and resource investments that no civilization on Earth has made or is currently planning to make. Every single propulsion system that has actually been built and flown produces travel times to Alpha Centauri measured in tens of thousands of years or more. Every propulsion system that could theoretically reduce the journey to centuries or decades has never left the drawing board. This is not a funding problem or a political problem. It is a physics and engineering problem of the deepest kind. The energy required to accelerate even a modest spacecraft to interstellar velocities is so vast that it dwarfs the entire energy budget of most nations. Consider the energy arithmetic directly. Kinetic energy scales with the square of velocity. To accelerate a single kilogram of payload to just 1% of the speed of light, roughly 3,000 kilometers per second, requires approximately 4.5 trillion joules of kinetic energy. That is equivalent to the energy released by roughly 1 kiloton of TNT for 1 kilogram. Now scale that up. A 1,000 kilogram spacecraft requires 4.5 quadrillion joules, equivalent to roughly 1 megaton of TNT. A full-scale thermonuclear weapon, scale to 100,000 kilograms, the minimum plausible mass for a crewed vehicle, and you need 450 quadrillion joules just to reach 1% of light speed. And 1% of light speed still means a journey to Alpha Centauri of over 400 years. To reach 10% of light speed, the energy requirement per kilogram increases by a factor of 100. Now, a 1,000 kilogram probe requires 450 quadrillion joules, comparable to the total annual electricity production of a mid-sized industrial nation. A crewed vehicle at 10% of light speed demands energy reserves approaching half the total annual energy consumption of the United States for a single mission, with no guarantee of deceleration at the other end. These are not speculative numbers. They follow directly from E equals 1/2 mv squared, the most elementary equation in classical mechanics. The energy cost of interstellar speed is not a mystery. It is a mathematical certainty, and it is ruinous. This brings us to what is perhaps the most sobering realization of all. Alpha Centauri is the nearest star system. It is the shortest possible interstellar crossing. And even this minimal distance defeats every propulsion technology that currently exists. Not because our engineers are incompetent, not because our scientists lack imagination, but because the distance is so large and the energy requirements of crossing it are so extreme that the entire enterprise lies beyond the current capability of human civilization. When people hear that Alpha Centauri is only 4.24 light-years away, they unconsciously compare it to the vast scale of the galaxy and feel reassured. It is close, they think, relatively speaking. But relatively speaking is the language of astronomers, not engineers. An astronomer can say that Alpha Centauri is close and be correct within the context of stellar distances. An engineer who tries to build a mission to Alpha Centauri confronts a wall of physics that makes the word close meaningless. We have measured the distance with exquisite precision. We have pointed our fastest machines in its general direction. We have calculated, planned, theorized, and dreamed. And the result, after all of that effort, is a simple and devastating conclusion. At the speeds we can actually achieve, the nearest star system is not a destination. It is a boundary, a line drawn in empty space that separates the places humanity can reach from the places it cannot. But what if we could go faster? Not a little faster, not twice as fast or 10 times as fast. What if we could go thousands of times faster, reaching significant fractions of the speed of light? That is the promise held out by the most ambitious propulsion concepts ever proposed. They offer speeds that would shrink the crossing to decades instead of millennia, and they introduce a new category of problems that are, in their own way, just as terrifying as the timescales they replace. Suppose we solve the propulsion problem, not incrementally, not by squeezing another few percent out of an ion engine or strapping a slightly larger fuel tank onto a chemical rocket. Suppose we make a genuine leap. Suppose some future generation of engineers builds a spacecraft capable of travelling at 1% of the speed of light. That is 3,000 kilometers per second, roughly 176 times faster than Voyager 1, a velocity so extreme that nothing in the history of human engineering has come within a factor of 100 of it. What happens then? At 1% of light speed, the journey to Proxima Centauri takes approximately 424 years. That is a dramatic reduction from 74,000 years. It is no longer a geological epoch. It is a historical one. 424 years ago from today, the early 1600s, Galileo had not yet pointed his telescope at Jupiter. Shakespeare was still alive. The Jamestown colony in Virginia had not been established. A spacecraft launched at 1% of light speed would arrive at Alpha Centauri in the late 2400s, by which time the civilization that launched it might be unrecognizable or extinct. 424 years is better than 74,000. It is not good. No human lives that long. No government lasts that long. The oldest surviving nation-states on Earth are only a few centuries old, and most have undergone radical transformations in that time. A mission that requires 400 years of continuous operation, continuous communication, and continuous institutional support is not a mission anyone can plan with confidence. It is a bet placed on the survival and coherence of human civilization across a time span longer than the entire history of the United States, the British Empire, or the modern scientific enterprise. But let us continue pushing the speed upward. At 2% of light speed, 6,000 kilometers per second, the transit drops to about 212 years, still longer than any human lifetime. Still longer than the continuous existence of most institutions. At 5% of light speed, 15,000 kilometers per second, the journey shrinks to approximately 85 years. Now we are approaching something that a human born at the moment of launch might, with extraordinary longevity, live to see completed. An infant placed aboard at departure could theoretically arrive as an elderly person, assuming the life support systems, the radiation shielding, the food production, the medical facilities, and every other system required to sustain a human life in deep space functioned flawlessly for nearly 9 decades. At 10% of light speed, 30,000 kilometers per second, the crossing takes roughly 43 years. This begins to feel like a real mission duration. It is comparable to the career span of a scientist or the operational lifetime of a major institution. A researcher who helped design the mission in her 30s might live to see the data return in her 70s. A probe launched with autonomous instruments could transmit findings to an engineering team that still remembers what the mission was for. 43 years is long, but it is not civilizationally long. It is biographically long. It fits within the architecture of a single human life. At 20% of light speed, 60,000 kilometers per second, the journey takes approximately 21 years. This is the speed that the Breakthrough Starshot project targeted when it was announced in April of 2016. 20% of light speed, a crossing to Proxima Centauri in just over 2 decades. Add 4.24 years for a return signal travelling at light speed, and the total time from launch to first data received on Earth comes to about 25 years. A generation, a career, a mortgage. The timescale finally drops into the range where it feels conceivable, where a project manager could sign the funding paperwork and reasonably expect to attend the data analysis meeting. This is the speed where interstellar travel begins to look possible on paper, and this is exactly where the next layer of problems reveals itself. Breakthrough Starshot was the most ambitious interstellar travel initiative ever backed by serious funding. Announced by the Israeli-American entrepreneur Yuri Milner, with $100 million in initial research funding, endorsed by the late Stephen Hawking, and supported by an advisory board that included some of the world's leading physicists and engineers, the project aimed to demonstrate a proof of concept for light-driven nanocrafts that could be accelerated to 20% of light speed using a ground-based laser array. The basic idea was elegant: build a phased array of lasers with a combined output of up to 100 gigawatts. Launch a mothership carrying thousands of gram-scale probes, each attached to a meter-scale reflective sail, into high Earth orbit. Then fire the laser array at each sail for approximately 10 minutes, accelerating the tiny craft to 20% of light speed through pure radiation pressure. The probes would coast to Alpha Centauri in about 20 years, perform a brief flyby, snap photographs, and transmit their data back to Earth using their sails as antennas. The concept violated no known laws of physics. It relied on technologies that existed in primitive forms: laser arrays, light sails, miniaturized electronics, and extrapolated them to scales that were ambitious but not physically impossible. It was, in the language of its proponents, engineering rather than science fiction. The physics worked. The question was whether the engineering could be made to work within a reasonable timeframe and budget. As of September 2025, Scientific American reported that the Breakthrough Starshot project appeared to be on indefinite hold. According to the physicist Philip Lubin, one of the project's key researchers, approximately $4.5 million of the proposed $100 million had been spent on about 30 research contracts. No prototype laser array had been built, no light sail had been tested at interstellar relevant scales, no Starship nanocraft had been launched on an interstellar trajectory. The project's leadership declined interview requests, and a promised status report had not appeared by the time the reporting went to press. Breakthrough Starshot was not formally cancelled. It simply stopped moving forward, quietly, without the fanfare that had accompanied its launch. This outcome is not a judgment on the people involved, many of whom are brilliant scientists doing important theoretical work. It is a judgment on the scale of the challenge. Even the most favourable version of interstellar propulsion, light sails accelerated by lasers, with no onboard fuel, with payloads measured in grams rather than kilograms, with no deceleration at the destination, with no return trip, still requires a laser installation producing 100 billion watts of coherent steerable power. For comparison, the total electrical generating capacity of the United States is roughly 1.2 trillion watts. Breakthrough Starshot's laser array would need to produce roughly 8% of America's total electrical output and focus it into a beam for 10 minutes per launch. The infrastructure required to build, power and operate such an array would be among the largest engineering projects in human history. And the laser array is only the beginning. The light sail must survive acceleration forces on the order of tens of thousands of times Earth's gravity. It must be reflective enough to absorb momentum from the laser without melting. It must maintain its shape and orientation during the acceleration phase, with precision measured in microns. The Starship payload must include cameras, power supply, navigation systems, communication equipment, and photon thrusters, all within a mass budget of roughly 1 gram. The communication link back to Earth must function across 4.24 light-years, using a sailor's antenna no larger than a few meters across, transmitting to receivers that do not yet exist at sufficient sensitivity. Each of these challenges is individually formidable. Together, they represent an engineering program that would require decades of development and budgets comparable to the largest scientific experiments ever undertaken, on the order of tens of billions of dollars. Breakthrough Starshot's $100 million was research funding, not construction funding. It was the budget for studying whether the concept might work, not for building it. And even if Breakthrough Starshot had succeeded brilliantly, the mission it envisioned was extraordinarily limited. A gram-scale probe travelling at 20% of light speed cannot slow down. There is no onboard fuel for deceleration. There is no mechanism for entering orbit around Proxima Centauri or any other body in the Alpha Centauri system. The probe screams through the system at 60,000 kilometers per second, and the entire close approach window during which it can photograph anything useful lasts for roughly a few hours at most. Everything the probe observes must be captured in that brief window and transmitted back to Earth across 4.24 light-years, using a communication system with a power budget measured in milliwatts. The data return from such a flyby would be scientifically valuable. Any image of an exoplanet taken from within the Alpha Centauri system would be historic. But the mission profile is closer to a bullet passing through a room and snapping a photograph than to an exploration in any meaningful sense. There is no lingering, no follow-up, no close inspection, no sample collection, no possibility of adjusting the trajectory based on what the probe finds. It is a one-shot, one-glance encounter with a star system 40 trillion kilometers away, and even this minimal achievement requires technology that does not yet exist. Let us now move beyond light sails and consider what faster speeds demand in terms of energy, because the energy problem is the true gatekeeper of interstellar travel, and it becomes more punishing with every increment of velocity. The kinetic energy of a moving object scales with the square of its velocity. Double the speed and the energy requirement quadruples. Triple the speed, and it increases 9-fold. This relationship is brutal at interstellar velocities. We calculated earlier that accelerating a single kilogram of payload to 1% of light speed requires approximately 4.5 trillion joules, roughly equivalent to 1 kiloton of TNT. For a 1,000-kilogram spacecraft, that becomes 4.5 quadrillion joules. Let us extend that calculation upward. At 5% of light speed, the kinetic energy of the same 1,000-kilogram spacecraft reaches approximately 112 quadrillion joules. That is equivalent to roughly 27 megatons of TNT, comparable to the most powerful nuclear weapons ever detonated. For a spacecraft that weighs about as much as a compact car, at 10% of light speed, the energy climbs to approximately 450 quadrillion joules, that is roughly 107 megatons, exceeding the yield of the largest thermonuclear weapon ever tested. For 1 metric ton of payload, at 20% of light speed, the Breakthrough Starshot target, the energy per kilogram of payload, reaches approximately 1.8 quadrillion joules. For a gram-scale starship, this is manageable. The kinetic energy imparted to the craft during the 10-minute laser push is on the order of 2 terajoules, roughly the energy released by a half-kiloton explosion. Intense but not civilizationally prohibitive, provided you have a 100 gigawatt laser array. But now imagine scaling up. Suppose you want to send not a gram-scale chip but a real spacecraft, something with instruments weighing tens of kilograms, or a probe weighing hundreds of kilograms, capable of decelerating and entering orbit, or a crewed vehicle weighing tens of thousands of kilograms, capable of sustaining human life for the journey. The energy requirements explode. A 100 kilogram probe at 20% of light speed requires approximately 1.8 times 10 to the 17th joules. That is roughly the annual electricity output of a mid-sized European country. A 10,000 kilogram probe, comparable to a large robotic spacecraft like Cassini, requires approximately 1.8 times 10 to the 19th joules. That exceeds the total annual energy consumption of many nations. A 100,000 kilogram crewed vehicle at 20% of light speed demands roughly 1.8 times 10 to the 20th joules, on the order of the entire world's annual energy consumption concentrated into a single propulsion event. And these calculations assume perfect efficiency, every joule of energy converted into kinetic energy of the spacecraft with no losses. Real propulsion systems waste enormous amounts of energy as heat, exhaust, radiation, and structural stress. Realistic efficiency factors might reduce the usable fraction to 10 or 20%, multiplying the total energy requirement by a factor of 5 to 10. The energy barrier does not soften at higher speeds, it hardens. Every additional percentage point of light speed costs dramatically more energy than the last. The curve is not linear. It is parabolic, rising ever more steeply as speed increases. And at velocities approaching a significant fraction of light speed, relativistic effects begin to add additional penalties as the effective mass of the spacecraft increases according to the Lorentz factor, demanding still more energy for each increment of velocity. This is why propulsion is not simply an engineering problem waiting for a clever solution. It is a problem embedded in the fundamental structure of physics. The energy cost of interstellar speed is dictated by laws that cannot be circumvented, negotiated, or innovated around. You can change the propulsion technology, you can improve efficiency, you can reduce spacecraft mass, but the kinetic energy equation remains, and it sets a floor on the energy required that no technology can breach. But energy is only half of the velocity problem. There is a second half that most discussions of interstellar travel quietly ignore, and it may be even more devastating than the first. It is the problem of stopping. Every energy figure discussed so far assumes a one-way acceleration. The spacecraft reaches its cruise velocity and then coasts to the destination at constant speed. This is the architecture Breakthrough Starshot adopted. Accelerate and never slow down. But a flyby is not a mission in any scientifically complete sense. If you want to enter orbit around a star or a planet, if you want to land on a surface, if you want to linger and observe for months or years, you must decelerate. And deceleration, in the merciless arithmetic of rocketry, is not a minor addition to the energy budget. It approximately doubles it at a minimum, and under realistic conditions, the penalty is far worse than doubling. The reason is the Tsiolkovsky rocket equation, the foundational law governing all reaction-based propulsion. The equation states that the velocity a rocket can achieve depends on two things: the exhaust velocity of its propellant and the ratio of its total mass at launch to its mass after all the fuel has been burned. To achieve higher velocities, you need exponentially more fuel relative to your payload. This relationship is not linear. It is logarithmic, which means that every additional increment of velocity requires a disproportionately larger amount of fuel. Now consider what deceleration means in this framework. A spacecraft that accelerates to 10% of light speed and then needs to stop at its destination must carry enough fuel not only to reach cruise velocity, but also to cancel that velocity entirely upon arrival. The fuel required for deceleration must itself be carried during the acceleration phase, which means it must also be accelerated to cruise speed. That additional fuel mass demands still more fuel to accelerate it, which demands still more fuel in turn. The rocket equation compounds this penalty exponentially. For a spacecraft using onboard reaction propulsion at 10% of light speed, the fuel-to-payload mass ratio can reach into the thousands or tens of thousands, depending on the exhaust velocity of the propulsion system. A spacecraft designed to accelerate and then decelerate is not a vehicle that carries some extra fuel. It is a vehicle that is almost entirely fuel, with the actual payload representing a tiny fraction of the total launch mass. This exponential penalty is why Breakthrough Starshot chose a flyby architecture. Decelerating a gram-scale probe from 20% of light speed using any known onboard propulsion method would require a fuel mass so large that the entire concept collapses. The probe would need to carry many times its own mass in propellant, negating the advantage of being lightweight in the first place. And even if a suitable propellant existed, the sail-based acceleration method provides no mechanism for slowing down at the destination. The laser is on Earth. It pushes the sail away. There is no laser at Alpha Centauri to push from the other direction. Some proposals have explored using the destination star's own light pressure to decelerate a light sail, or using magnetic fields to brake against the interstellar medium. These concepts are theoretically interesting but remain unproven and face severe practical limitations. Stellar light pressure is far too weak to decelerate a probe, arriving at 20% of light speed. Magnetic braking would require enormous superconducting structures and would work only at much lower velocities. The deceleration problem means that every energy figure discussed so far applies only to the simplest possible mission profile: a one-way, non-stop flyby with no ability to slow down, orbit, or return. Any mission that aspires to do more than scream through the Alpha Centauri system at 60,000 kilometers per second and snap a photograph must carry the energy not just to get there, but to stop there. And the energy cost of stopping is not additive, it is multiplicative. It does not merely double the challenge. Under realistic mass ratios, it can increase the total energy requirement by a factor of 10 or more. This is why the distinction between a flyby and an actual exploration mission matters so profoundly. A flyby is what you do when the distance has already beaten you, and you are willing to accept a glimpse instead of a visit. An exploration mission, one that enters orbit, deploys instruments, and studies the system for years, requires solving the deceleration problem. And solving the deceleration problem at interstellar velocities requires energy budgets that dwarf even the already staggering figures needed for acceleration alone. Now let us add the dimension that most interstellar travel discussions conveniently omit: communication delay. The speed of light is not just a barrier to travel, it is a barrier to information. A radio signal or a laser pulse sent from Alpha Centauri to Earth, or from Earth to Alpha Centauri, travels at exactly the speed of light. No faster, no exceptions. The one-way communication time is 4.24 years. A round-trip question and answer takes 8.48 years. This means that any probe arriving at Alpha Centauri operates in total communication isolation for the duration of its flyby. Ground controllers on Earth cannot steer it in real time. They cannot adjust its camera pointing based on what it sees. They cannot command it to investigate an unexpected feature or avoid an unanticipated hazard. Every action the probe takes during its encounter must be pre-programmed before launch or decided autonomously by onboard software. The probe is on its own. For a Breakthrough Starshot style flyby, this limitation is manageable. The probe's task is simple: point a camera at whatever is in front of you and transmit the data. But for any more ambitious mission, the communication delay becomes crippling. Suppose a future probe is designed to enter orbit around Proxima Centauri b, the Earth-sized planet in Proxima's habitable zone. Orbital insertion requires precise timing, precise velocity adjustments, and real-time response to conditions that cannot be predicted from Earth. If the probe encounters an unexpected dust ring, a debris field, a magnetic environment that interferes with its instruments, it must diagnose and respond to the problem without any input from mission control. The answer to any question it sends back to Earth will not arrive for over 8 years. Now scale this up to a crewed mission. Imagine human beings arriving at Alpha Centauri after a journey of decades. They enter the system, begin observations, encounter something unexpected. A medical emergency, a mechanical failure, a navigational hazard. They send a message to Earth describing the problem and requesting guidance. The message arrives on Earth 4 years and 3 months later. Engineers study the problem, formulate a solution, and transmit instructions. Those instructions arrive at Alpha Centauri another 4 years and 3 months after that. More than 8.5 years have elapsed since the crew first reported the problem. Whatever the emergency was, it has long since resolved itself, one way or another. The crew lived or died, succeeded or failed, entirely on their own resources. This is operational isolation of a kind that no human mission has ever faced. The Apollo astronauts on the Moon experienced a communication delay of about 1.3 seconds, annoying but manageable. A crew on Mars would face delays of 4 to 24 minutes depending on orbital positions, challenging but survivable with autonomous systems and pre-planned contingencies. A crew at Alpha Centauri would face delays of over 4 years. That is not a communication challenge, that is abandonment. The crew is functionally disconnected from Earth. They cannot call for help. They cannot receive supplies. They cannot be rescued. They are the most isolated human beings who have ever lived, separated from home not just by distance but by time. The psychological implications are rarely discussed, but potentially severe. Human beings evolved as social creatures embedded in communities. Even astronauts on the International Space Station, orbiting just 400 kilometers above Earth, report feelings of isolation and psychological strain during 6-month missions. Submarine crews on 90-day patrols experience measurable psychological effects. Antarctic researchers isolated for the winter dark season show increased rates of depression and cognitive impairment. Now imagine a crew that knows, with mathematical certainty, that no help can arrive for decades, that no message from loved ones will reach them in less than 4 years, that every decision, every crisis, every moment of the mission depends entirely on the resources and the people aboard. This is not exploration in any historical sense. When Magellan's crews sailed around the world, they could stop at ports, trade for supplies, interact with local populations. When Antarctic explorers reached the pole, they knew rescue ships were months away, not decades. The crew of an interstellar mission has no ports of call, no supply ships, no rescue missions. No one is coming. The stars are too far apart. And this isolation applies not just to crewed missions. Even robotic probes at Alpha Centauri are operationally alone in a way that no previous space mission has been. Every Mars rover eventually receives updated software, new mission plans, troubleshooting commands from Earth. The delay is minutes, not years. At Alpha Centauri, a robotic probe must be programmed with enough intelligence and enough contingency planning to handle every conceivable situation autonomously. It must be, in effect, a fully independent scientific agent capable of making its own decisions about what to observe, how to respond to anomalies, and how to prioritize its limited resources. The artificial intelligence required for such autonomy does not currently exist. We are decades away from building software that can replicate the judgment of a skilled mission controller, and even if we build it, there is no way to test it against the actual conditions at Alpha Centauri before the probe arrives. There is another dimension to the communication problem that cuts even deeper than delay. It is bandwidth. The amount of data a probe can transmit back to Earth depends on its transmitter power, its antenna size, the receiver sensitivity on Earth, and the distance the signal must travel. Over interstellar distances, the achievable data rate drops to absurdly low levels. A Breakthrough Starshot-style nanocraft, transmitting with milliwatts of power across 4.24 light-years, might manage a data rate of a few bits per second under the most optimistic assumptions. Sending a single high-resolution photograph at that rate could take weeks or months. Even a larger probe with a dedicated high-power transmitter and a large antenna would face severe bandwidth constraints. The data rates achievable across interstellar distances with foreseeable technology are measured in bits per second, not megabits. A mission that spent years observing the Alpha Centauri system might accumulate terabytes of data but require decades to transmit it all home. The scientific return of an interstellar mission is throttled not just by what the probe can observe, but by how much of what it observes can be communicated back across the void. This is the compound reality of interstellar distance. It is not one problem. It is a cascade of interlocking problems, each feeding into the next. The distance demands extreme speed. Extreme speed demands extreme energy. Extreme energy demands either tiny payloads or civilization-scale infrastructure. Tiny payloads limit scientific return. Larger payloads multiply the energy cost beyond current capability. Any speed, short of light speed, imposes years of communication delay. Communication delay eliminates real-time control. Eliminated real-time control demands autonomous operation. Autonomous operation demands artificial intelligence that does not yet exist. And even the data that an autonomous probe collects can only trickle back to Earth at rates that would have embarrassed a 1990s dial-up modem. Every one of these problems exists at Alpha Centauri, the nearest star, not at some distant target 10 or 50, or 100 light-years away, at the easiest destination in the interstellar catalogue, 4.24 light-years, 40 trillion kilometers, and we have not solved any of these problems. Not one. The temptation at this point is to retreat into optimism, to say that technology advances exponentially, that what seems impossible today will be routine tomorrow, that the Wright brothers could not have imagined jet airliners, and therefore we should not assume our limitations are permanent. There is some truth in this. Technology does advance. Problems that seemed intractable often yield to ingenuity given enough time. But the interstellar distance problem is not like the problem of powered flight. The Wright brothers needed to generate enough lift to overcome Earth's gravity at low speeds. The physics was well understood. The engineering gap was narrow. Interstellar travel requires generating enough energy to cross a gulf so vast that light itself needs years to do it. The engineering gap is not narrow. It spans orders of magnitude. The most optimistic propulsion concepts require energy outputs that exceed the total current production of human civilization. The physics is not waiting for a clever trick. The physics is the problem. And Alpha Centauri is patient. It does not care about our optimism or our timeline. It sits in the southern sky, brilliant and beautiful and exactly 4.24 light-years away, neither approaching nor receding at any rate that matters on human timescales. It will be there when we solve these problems, if we solve them. It will be there if we do not. The distance is what it is. 40 trillion kilometers of nothing, waiting for a species that has never crossed more than a fraction of a single % of it. What remains to be reckoned with is not whether we can someday reach Alpha Centauri. That question belongs to the future. What remains is what Alpha Centauri's distance tells us right now, today, about the kind of universe we live in and the kind of challenge interstellar space actually represents. That reckoning begins with a simple observation. This is the nearest star system, and it already demands more than we have. Everything else is farther. In August of 2025, a team of astronomers using NASA's James Webb Space Telescope published what may become one of the most consequential findings in the history of exoplanet science. Using the telescope's mid-infrared instrument, they detected a point source of light near Alpha Centauri A that is consistent with a gas giant planet roughly the mass of Saturn, orbiting its star at approximately twice the distance between Earth and the Sun. The candidate world, if confirmed, would sit within Alpha Centauri A's habitable zone. It would be the nearest, coldest, oldest, and lowest mass planet ever directly imaged beyond our solar system. The papers describing the discovery were accepted for publication in the astrophysical journal Letters. The finding was greeted with enormous excitement and enormous caution in equal measure because confirmation remains pending. The story of this detection is instructive. The initial observation was made in August of 2024. The team then conducted 2 follow-up observations in February and April of 2025. In both cases, the candidate planet was not recovered. It had seemingly vanished. But computer simulations of millions of potential orbits revealed that in roughly 52% of gravitationally stable orbital configurations, the planet would have been too close to Alpha Centauri A to be distinguished from the star's glare during those follow-up windows. The disappearance was not evidence against the planet's existence. It was consistent with a world on an elliptical orbit that had simply moved behind or in front of its star from our line of sight. The team also folded in a tantalizing 2019 observation from the European Southern Observatory's Very Large Telescope, which had detected a candidate point source at a slightly different position near Alpha Centauri A. If both detections represent the same object seen at different points in its orbit, the combined data suggest a Saturn mass planet with an orbital period of roughly 1.5 to 2.5 years and an orbital eccentricity of about 0.4. This candidate is not confirmed. It may turn out to be an instrumental artifact, a clump of zodiacal dust, or a statistical fluke. The researchers themselves are careful to describe it as a candidate, not a discovery. The next opportunity to test the finding comes in August of 2026, when the planet, if real, should reappear in a position detectable by the James Webb Space Telescope. If it does, the confirmation would be historic. If it does not, the candidate may join the long list of promising signals that ultimately faded into noise. But the mere plausibility of this finding transforms the emotional stakes of the distance problem. Alpha Centauri is no longer just the nearest star system in the abstract. It may contain a gas giant orbiting within the habitable zone of a sun-like star, and where gas giants orbit in habitable zones, moons may exist. Moons with atmospheres, moons with liquid water, moons with the raw ingredients for chemistry that, on at least one world we know of, eventually produced life. This is not speculation about distant galaxies or exotic stellar systems hundreds of light years away. This is the star system next door, the one you can see with your unaided eye on a clear southern night, the one whose light takes only 4 years to reach your retina, and the James Webb Space Telescope is telling us that it may harbour a planetary system far richer and more complex than we previously knew. Proxima Centauri, the closest individual star, already hosts at least 2 confirmed planets. Proxima Centauri b, discovered in 2016, is roughly Earth-sized and orbits within its star's habitable zone, the region where liquid water could theoretically exist on a rocky surface. Proxima Centauri d, a much smaller world with a mass of roughly a quarter of Earth's, was detected in 2022 and confirmed in 2025. A third planet, Proxima Centauri c, a possible super-Earth or mini-Neptune orbiting much farther out, has been proposed, but remains disputed as of 2025, with observations from the NIRPS spectrograph unable to confirm it. But even the most promising of these worlds, Proxima Centauri b, carries a burden of scientific uncertainty that no telescope can fully resolve from a distance of 4.24 light-years. The planet orbits within Proxima Centauri's habitable zone, yes. But habitable zone is a term defined purely by temperature, the range of orbital distances where liquid water could exist on a rocky surface given certain atmospheric assumptions. It says nothing about whether a planet actually has liquid water, or an atmosphere, or any of the conditions that biology requires. And in the case of Proxima b, there are serious reasons to doubt that it does. Proxima Centauri is not a calm, steady star like our Sun. It is an M-dwarf flare star, one of the most magnetically active stellar types known. It produces violent flares on a regular basis, sudden eruptions that can increase the star's brightness by a factor of several within minutes. and bathe its surrounding space in intense ultraviolet and X-ray radiation. In 2018, astronomers detected a superflare from Proxima Centauri that was roughly 10 times more energetic than the most powerful solar flares ever recorded from our Sun. These events are not rare. They occur multiple times per year, sometimes multiple times per month. Any planet orbiting close enough to Proxima Centauri to receive warmth sufficient for liquid water is also close enough to be repeatedly irradiated by these outbursts. The implications for habitability are severe. Intense ultraviolet radiation can destroy organic molecules on a planetary surface. Repeated X-ray flares can strip away atmospheric gases over geological timescales, eroding whatever protective blanket a planet might have started with. Computer models, simulating the long-term atmospheric evolution of Proxima b, suggest that the planet may have lost its atmosphere entirely within the first few 100 million years of its existence, leaving a bare, irradiated rock with no protection against the harsh radiation environment. Some models allow for atmospheric survival under specific conditions, such as a strong planetary magnetic field or an unusually thick initial atmosphere, but these conditions are speculative. We do not know whether Proxima b has a magnetic field. We do not know what its initial atmosphere looked like. We do not know if any atmosphere remains today. There is also the problem of tidal locking. Because Proxima b orbits so close to its star, completing one orbit in roughly 11 days, gravitational interactions have almost certainly synchronized its rotation with its orbit. This means one hemisphere permanently faces the star in eternal daylight, while the opposite hemisphere faces away in eternal darkness. The temperature contrast between the two sides could be extreme, scorching heat on the day side and deep freezing cold on the night side. Whether atmospheric circulation could redistribute heat effectively enough to maintain habitable conditions on some portion of the surface is an open question that atmospheric models answer differently depending on their assumptions. The honest scientific assessment of Proxima Centauri b, as of 2026, is this. It is an Earth-sized planet in the habitable zone of the nearest star, and it might be a sterile, atmosphere-stripped rock baked by stellar radiation on one side and frozen solid on the other. It might also be a world with a thick atmosphere, active weather systems, and liquid water on its surface. We do not know. The data we can collect from Earth, even with the most powerful telescopes available, cannot definitively distinguish between these two scenarios. Resolving the question almost certainly requires observations from within the system, from a probe close enough to analyze the planet's atmosphere, surface, and magnetic environment directly. This is the cruelest dimension of the distance problem. The nearest potentially habitable planet may or may not be habitable at all, and the only way to find out for certain is to cross 40 trillion kilometers of empty space to go and look. The question is answerable. The distance makes it unanswerable from here. So the nearest star system to our Sun contains at minimum 2 confirmed planets around Proxima Centauri and a strong candidate planet around Alpha Centauri A. There may be more. Radial velocity surveys have placed increasingly tight constraints on undetected planets in the system, ruling out large worlds at many orbital configurations, but the sensitivity limits still leave room for smaller terrestrial planets that current instruments cannot detect. The Alpha Centauri system may be home to an entire family of worlds, some rocky, some gaseous, some potentially habitable, all orbiting within a stellar system that is practically on our cosmic doorstep. We can see these worlds, we can measure their masses, we can constrain their orbits. Within the next decade, we may be able to characterize their atmospheres using spectroscopy, searching for chemical signatures like oxygen, methane, carbon dioxide, or water vapor that might indicate biological activity. The James Webb Space Telescope and its successors, including the Nancy Grace Roman Space Telescope, expected to launch in 2027, are specifically designed for this kind of work. The era of studying exoplanet atmospheres in the Alpha Centauri system is not a distant fantasy. It is beginning now. And this is precisely where the distance becomes not just an obstacle but a source of something approaching existential frustration. We can see the planets. We can study them from afar. We can learn their sizes, their orbits, their temperatures, perhaps even their atmospheric compositions, but we cannot visit them. We cannot send a probe that arrives within a human lifetime using any technology that currently exists. We cannot land an instrument on their surfaces. We cannot collect a sample of their soil or their atmosphere. We cannot confirm with certainty whether any of these worlds harbour life, because the definitive detection of biology almost certainly requires being there, in the system, with instruments sensitive enough to analyse surface chemistry or subsurface oceans at close range. The universe has placed potentially habitable worlds at the nearest possible stellar address, and then surrounded that address with 40 trillion kilometres of impassable void. The invitation is visible. The door is locked. This tension between visibility and accessibility is not unique to Alpha Centauri, but it is most acute there because the stakes are highest. Alpha Centauri is the proving ground. If we cannot reach the nearest star system, we cannot reach any star system. Every other target in the interstellar catalogue is farther away, most of them vastly farther. Barnard's star, the next nearest single star system, is roughly 6 light-years away, nearly 50% farther than Proxima Centauri. Wolf, 359, is about 7.9 light-years distant. Lalande, 21,185, is over 8 light-years. Sirius, the brightest star in the sky, and a system that has fascinated astronomers for millennia, is 8.6 light-years away, more than double the distance to Alpha Centauri. And these are still our immediate stellar neighbours. The nearest star with a confirmed Earth-like planet in its habitable zone, other than Proxima Centauri b, could easily be tens or hundreds of light-years away. The galaxy is 100,000 light-years across. The overwhelming majority of its 400 billion stars are separated from us by distances that make Alpha Centauri's 4.24 light-years look like a rounding error. If the nearest star already requires 74,000 years at current speeds or civilization-scale energy investments at advanced speeds, then the broader galaxy is not a frontier. It is a prison. The bars are made of distance, and they are spaced at light-years. This is the realization that the distance to Alpha Centauri ultimately forces. It is not just that one particular star is far away, it is that the spacing between stars, the fundamental architectural parameter of the galaxy, is set at a scale that dwarfs the capabilities of any technology humanity has ever built or is currently building. The galaxy is not a dense web of nearby destinations waiting to be explored. It is an ocean of emptiness, containing tiny, scattered islands, separated by gulfs that light itself takes years to cross. The numbers bear this out with uncomfortable clarity. The average distance between neighbouring stars in our region of the Milky Way is roughly 4 to 5 light-years. Alpha Centauri's distance is not an anomaly. It is typical. The nearest star happens to be about as far away as stars generally are from each other in this part of the galaxy. There is no closer option hiding behind a dust cloud. There is no secret stellar neighbour at half a light-year that surveys have somehow missed. The density of stars in the solar neighbourhood is what it is, and it places even the nearest neighbours at distances that dwarf anything in human experience. Closer to the galactic centre, stellar densities increase. Stars in the core regions of the Milky Way can be separated by fractions of a light-year. In globular clusters, the average distance between stars can be as small as 1/10 of a light-year, but even these reduced spacings still represent trillions of kilometres. And the galactic core and globular clusters pose their own challenges: intense radiation, gravitational instability, and stellar environments so hostile that habitability becomes questionable. Denser stellar neighbourhoods are not necessarily easier places to conduct interstellar travel. They are simply places where the void between islands is slightly less vast. Let us now confront the most uncomfortable implication of all. Alpha Centauri is the easiest interstellar target humanity will ever have. This is not a pessimistic framing. It is a geometric fact. The nearest star system is, by definition, the one that requires the least energy, the shortest travel time, and the smallest communication delay to reach. Every other star system requires more of all three. If the nearest target already exceeds our capability, then the difficulty curve for interstellar travel does not start at manageable and climb to challenging. It starts at overwhelming and climbs to incomprehensible. Consider what a mission to a star just 10 light-years away would require. The travel time at Voyager speeds would exceed 175,000 years. At 1% of light speed, roughly 1,000 years. At 10% of light speed, 100 years. The energy requirements scale linearly with distance for a given velocity, so a mission to a star at 10 light-years demands roughly 2.4 times the energy of a mission to Alpha Centauri at the same speed. The communication delay doubles to over 20 years round trip. Every problem we have already examined – energy cost, transit time, communication isolation, material degradation, navigational precision – becomes proportionally worse, and 10 light-years is still the immediate neighbourhood. The nearest star with characteristics closely matching our Sun, one that might plausibly host a planetary system like our own, could be 20 or 30 light-years away. A mission to such a star, at 10% of light speed, would take 2 to 3 centuries. The communication round trip would span 40 to 60 years. The energy budget would be 5 to 7 times that of an Alpha Centauri mission. We are already deep into the realm of multi-generational timescales and multinational energy commitments, and we have barely left the solar neighbourhood. Push farther out. The nearest large spiral arm of the galaxy, the Perseus arm, lies roughly 6,000 light-years from our position in the Orion arm. The galactic centre is 26,000 light-years away. The far edge of the Milky Way is roughly 50,000 light-years beyond that. At 10% of light speed, the most optimistic sustained velocity for any propulsion concept seriously studied, a journey to the galactic centre would take 260,000 years. A crossing of the full galaxy would take roughly 1 million years. These are not travel times, they are evolutionary timescales. Species change, go extinct, and are replaced in less time than a crossing of the galaxy at any speed humans have seriously contemplated. The galaxy is not a place you cross, it is a structure you inhabit locally, like an organism confined to a single organ system within a body that spans continents. We can observe the whole body. We can map its structure, measure its mass, study its dynamics. But we live in one tiny neighbourhood, and the distances to other neighbourhoods are so extreme that they impose a kind of cosmic quarantine. Not a quarantine enforced by any authority, a quarantine enforced by the geometry of space itself. This is what Alpha Centauri teaches us, and it is a lesson that no amount of technological optimism can fully soften. The universe is structured in a way that makes observation easy and visitation almost impossibly hard. We can see stars across the galaxy with modest telescopes. We can detect planets around stars hundreds of light-years away. We can study the atmospheres of worlds in other solar systems using spectroscopy. We can listen for radio signals from potential civilizations across thousands of light-years. Seeing is relatively easy. The universe is generous with its photons. But reaching is another matter entirely. Photons are massless. They travel at the speed of light by default. They cost nothing to send and nothing to receive. Spacecraft are not photons. They have mass. They require energy to accelerate. They carry instruments that degrade, structures that age, and, if crude, human beings who require food, water, air, and psychological stability. The cost of sending a physical object across interstellar distances is not comparable to the cost of receiving light from that same distance. The asymmetry is staggering. We can photograph a planet around Alpha Centauri using a telescope that costs $10 billion and orbits 1 million miles from Earth. We cannot visit that planet for any amount of money currently imaginable. There is a philosophical dimension to this asymmetry that deserves acknowledgement, though the point should be made with restraint. The universe appears to have been constructed or to have evolved through natural processes in a way that maximizes the visibility of its contents while minimizing access to them. Stars broadcast their light in all directions across billions of years. Planets reveal themselves through transits, gravitational wobbles, and infrared emission. Galaxies are visible across billions of light years. The cosmic microwave background preserves an image of the universe as it existed 13.8 billion years ago. Information flows freely across the cosmos at the speed of light. But matter does not. Matter is confined to its local gravitational well unless enormous energy is expended to move it elsewhere. The energy cost of moving matter between stars is so extreme that it functionally partitions the galaxy into isolated zones, each centered on a single star or star system, each separated from its neighbors by voids that are transparent to light but opaque to spacecraft. If you were designing a universe intended to frustrate interstellar civilizations while rewarding interstellar astronomers, you could hardly do better than the one we inhabit. The sky is full of destinations. The space between them is full of nothing. You can look wherever you want. You can go almost nowhere. Alpha Centauri crystallizes this truth more clearly than any other object in the sky. Precisely because it is the nearest star, it is the data point at the extreme minimum of the distance function. It is the most favorable case, the gentlest version of the interstellar distance problem, the one that every other star system makes harder, and it is already, by every engineering metric available, beyond our reach. This does not mean that interstellar travel is permanently impossible. Physics does not forbid it. The speed of light permits crossings of 4.24 light-years in as little as 4.24 years, and time dilation at relativistic speeds can compress the subjective experience of the journey for travelers aboard the spacecraft. There is no fundamental physical law that says a spacecraft cannot reach Alpha Centauri. There is only the practical reality that doing so requires energy, engineering, and institutional commitment on scales that no human civilization has ever demonstrated. Perhaps a future civilization will demonstrate them. Perhaps breakthroughs in fusion power, or antimatter production, or energy storage or laser propulsion, or some physics we have not yet discovered will shift the calculus enough to make a mission feasible. It would be arrogant to declare that the problem is unsolvable when the history of technology is littered with confident declarations of impossibility that were later overturned. But it would be equally arrogant to assume the problem will solve itself simply because we find it inconvenient. The distances between stars are not engineering challenges in the way that building a bridge or launching a satellite are engineering challenges. They are consequences of the fundamental geometry of the universe, set by the density of matter in the galactic disk, the average spacing of stellar formation, and the speed limit imposed by relativity. These are not parameters that technology adjusts. They are boundary conditions within which all technology must operate. Alpha Centauri is 4.24 light-years away. That distance was not chosen by nature to be convenient or inconvenient for human exploration. It is simply the distance at which the nearest star happens to have formed, 4.5 billion years ago, in a region of the galaxy where stellar densities are what they are. The distance carries no message. It implies no intention. It is indifferent to human ambition. And that indifference is perhaps the most important thing the distance teaches us. The universe does not adjust its scale to match the capabilities of its inhabitants. It does not arrange the stars at reachable intervals for the convenience of civilizations that happen to evolve on one of its trillions of rocky worlds. The spacing between stars is a physical fact, not a design feature. Whether we find that fact thrilling or terrifying depends on our expectations, not on the universe. What is certain is this: the distance to Alpha Centauri is not merely a large number. It is a statement about the kind of cosmos we inhabit, a cosmos where light travels freely but matter is trapped, where information flows at 300,000 kilometers per second, but spacecraft crawl at 17, where the nearest star blazes brilliantly in the southern sky, close enough to see with the naked eye, far enough to defeat every machine humanity has ever built. And the terrifying part is not the distance itself. 40 trillion kilometers is just a number. A number can be written on a page, spoken aloud, converted from one unit to another. What makes the distance terrifying is the context. This is not the distance to some remote, obscure stellar outpost on the far side of the galaxy. This is the distance to the nearest star, the absolute closest, the starting line, the easiest case, the floor. Everything beyond Alpha Centauri is farther. Every other interstellar destination, without exception, demands more energy, more time, more isolation, more risk, and more commitment than a journey to the star system that sits closer to us than any other. If the floor is already this high, the ceiling is beyond sight. That is what Alpha Centauri reveals. Not just a distance, a truth about the architecture of the galaxy. The stars are near enough to study. They are far enough to humble. And the nearest of them all, shining in Centaurus like a beacon, is already so far away that crossing the gap would be the single greatest physical achievement in the history of any civilization that accomplished it. 4.24 light years, 40 trillion kilometers, 25 trillion miles, 268,000 times the distance from Earth to the Sun, 74,000 years at the speed of Voyager, over 400 years at 1% of light speed, 21 years at 20% of light speed, using technology that does not exist, delivering a payload measured in grams for a flyby lasting hours, with a return signal arriving 4 years later. This is the nearest star, this is the easiest target, this is the beginning of interstellar space, and it is already almost beyond comprehension.